Hi. Uh, so in this video, we are going to start our journey into group theory. And the idea for this set of lectures is to understand group theory basically from the point of view of preparing for a master's in maths. So there are many students who might be preparing for a higher studies or higher degrees in maths. And a typical exam that they write is IIT JAM or something like that to get into a master's program. So this will be useful for students like that, like whoever is preparing for IIT JAM, say 2024. So what I want to do is create a set of resources for students like that, which will be available for free on YouTube, and basically cover the entire syllabus for masters in maths. So that includes basically group theory, calculus, multivariable calculus, real analysis, linear algebra, and some more topics there. So we will go through it in a sequential manner. We'll start off with group theory. And this lecture talks about the basic number theory that you require to understand group theory. Let's just begin. The first thing that we want to talk about here in number theory is the well ordering principle. That is a very important axiom that is required for proper analysis of group theory concepts. So, what is well ordering principle? It is very easily stated, but the proof of it is a little complicated because this is taken as an axiom. So, when we take something as an axiom, we assume that it is a self evident truth. We do not try to prove it because we will use this axiom to prove other concepts in number theory. So, right now, we'll not go get into the proof of this. We'll just describe what well ordering principle means. So, suppose A is a non-empty set of integers. Non-empty set of integers. Then A always has a least member. Then A has, when I say integers, this should be a non-empty set of positive integers. Positive integers. Then A has a least element. So think of any set of positive integers. Obviously, there will be an element which is the smallest integer in that set. So this principle seems to state a fact that is pretty obvious to most of us. If you have a non-empty set, any set of integers, positive integers, obviously there is an element which is the least element, right? Because integers follow the ordering property. Like any two integers, you can basically say which one is greater, which one is smaller, right? So this is the well ordering principle. We will see how it is used in future classes in group theory. For now, we'll move on. The next thing that we want to talk about is the division algorithm. I'm sure many of you are familiar with the algorithm. It is Euclid's division lemma. So how do we do this? So it says that let A be any integer and B is a positive integer. B is a positive integer. Then A can be written as BQ plus R. So A is equal to BQ plus R, where Q and R are integers. Q and R are integers, and 0 is less than equal to R is less than B. So basically, you are dividing A by B, and Q is the quotient, and R is the remainder. So everyone is probably familiar with this. The remainder must always be between 0 and less than B, right? Because if it was equal to B, then we would have done Q plus 1 into B, right? And R could have been 0. So that is the idea of the division lemma. Here, when you claim that there is a largest multiple of B less than A, we are using basically well ordering principle to claim this. When we say that there is a way to write A as BQ plus R and R will always be this between 0 and B, we are saying that we are using well ordering principle here. Now, the next thing that we can do with the division lemma is let A and B belong to natural numbers if A and B are relatively prime. If A and B are relatively prime, that means they have no common factors other than 1. If A and B are relatively prime, then there exist integers x and y such that ax plus by equals to 1. This is a special case of a more general property where you can say ax plus by is equal to GCD of A and B. But in this case, the GCD of A and B is 1 because they are relatively prime. By GCD, we mean greatest common divisor. I'm sure all of you are familiar with the concepts of GCD, LCM, and so on. So we are just right now trying to understand and set up the basics of number theory that we'll be using later. So I'm just going through these concepts quickly. Another idea that we can look at is let M and N be relatively prime. Relatively prime again. If M divides N times A, then M divides A. The idea is pretty obvious. If M is dividing the product of N and A, since we know that M and N are relatively prime, it cannot be that M is dividing N because the GCD of M and N is 1. So how is M going to divide NA if it cannot divide N? It must divide A, right? The formal proof of it can be done pretty easily. I will leave that to you. Right now, we are going to just list down these facts. Again, another similar property is let M and N are relatively prime if M divides K. This symbol stands for M divides K. If M divides K and N divides K, this is N divides K. So basically M and N are factors of K, right? Then we can say that Mn divides K, right? So again, the proof is pretty obvious. If M divides K, K can be written as M times P, where P is an integer. And similarly, K can also be written as N times Q, where Q is an integer, right? And basically, we can say that M and N will divide K because what is M and N? You can say K square. K square will be Mn PQ, right? And M and N will divide K because we can multiply PQ on both sides here. And we will say that PQ into Mn will divide K square. We can say PQ into Mn will divide K square. And therefore, Mn will also divide K. Another property that we'll look at is if P is a prime, and P divides AB, then either P divides A or P divides B. Again, if P divides AB, then P is a factor of A or B, either A or B. So that is what the statement is actually conveying, right? The fundamental theorem of arithmetic, that is something that is present in all basic number theory courses. Fundamental theorem of arithmetic says that every positive integer can be factorized. Every positive integer can be written as a product of primes, can be written as a product of primes. And the factorization is unique. If you discount the order of the primes, the factorization is unique. So there's only one way to write an integer as a product of prime numbers, as long as you ignore the order in which the prime numbers are written, right? Now, we will look at modular arithmetic, a little bit of basics of modular arithmetic. So we say A is congruent to B mod n if n divides A minus B. So this is the definition of congruency. So A is congruent to B mod n if n divides A minus B. Or you can say that A and B have the same remainder when divided by n. When divided by n. That is your basic congruency stuff. Now, what we can say is we can split the set of integers. This is the set of integers. This set of integers can be split into n disjoint sets. Split into n disjoint sets. What are these n disjoint sets? Let's label them as nz, nz plus 1, nz plus 2, and so on till nz plus n minus 1. And what is the meaning of these sets? So these are the n different remainders possible when you divide any integer by n. So suppose I pick n is equal to 5. I can say that my set of integers can be divided into 5 sets. One is 5z, one is 5z plus 1, 5z plus 2, 5z plus 3, 5z plus 4. These are the 5 sets. What are the meaning of these 5 sets? This is the set of all numbers that are divisible by 5. So this will include 5, 10, 15, 0, and so on. This is the set of numbers which leave remainder 1 when you divide by 5. So these numbers here will be 6, 11, 16, and so on. And this similarly, this will be 7, 12, 17, and so on. So the remainder is 2, remainder is 3, remainder is 4. There are no other types of integers. So always the set of integers can be split into n disjoint sets if you consider it modulo n, right? So these sets are actually called the residue classes of the integers modulo n. This is just terminology. I'm trying to get you familiar with the terms that you will require for group theory. So the definition here is stated like this. For any A belongs to Z, you can say A modulo n is nz plus A. So this is a set basically. The set A modulo n is the set of numbers like this. A minus 2n, A minus n, A plus n, A plus 2n, and so on. It is an infinite set of numbers which always leaves remainder A when you do division by in modulo n, right? So the numbers A plus n, A plus 2n will always leave remainder A when you are doing division modulo n. And this set is basically called the residue class, residue because it is a remainder class of A modulo n, right? So there are basically n residue classes of integers modulo n. integers modulo n. What are the residue classes? We wrote them down in the previous screen. So basically they are 0, 1, 2 till n minus 1. So we are dropping the subscript here, because we already understand that it is integers modulo n, and these are the residue classes. So 0, 1, 2, n minus 1, right? So these are the sets of numbers, sets of integers which leave remainder 0, which leave remainder 1 when you divide by n, right? So this is something that will come in handy as we go ahead in group theory. So we just want to set down our definitions in the first class. The next thing is some properties of congruences. So if A is congruent to B mod n and C is congruent to D mod n, then we can say that A plus C is congruent to B plus D mod n. And we can also prove that AC is congruent to BD mod n. So under congruent modulo n, the multiplication and addition operations are preserved. So you can add and multiply congruent numbers as long as they are congruent to each other in a regular way, right? Now we talk about what is the meaning of the Zn set. So Zn set was the set of integers modulo n, right? So set of integers modulo n. In this set, basically any integer, let's say n is 5, for example. If n is 5, what is z5? Z5 is the set of integers which form the residue classes 0, 1, 2, 3, 4, right? So any other integer will always end up either in one of these 5 residue classes, right? So what we can say is in Z5, you can always prove that A plus B is equal to B plus A, right? A plus 0 is equal to 0 plus A is equal to A. Also, A into B plus C is equal to AB plus AC. A into 1 is A. A into 0 is 0. So we can show all of these properties in this Zn set. So for example, let's try it out. So in Z5, can we add two numbers? So let's add 2 plus 3. 2 plus 3 is 0 in Z5, right? Because 2 plus 3 is 5, but 5 will fall in the 0 residue class, right? Similarly, we can show that 3 plus 2 is also 0. So we are proving this property here. A plus B is B plus A, right? Also, we can show that A into B plus C is AB plus AC. How? So let's try a couple of numbers. Let's say A is 1, B is 3, C is 4, right? So what is A into B plus C? That is what? A into 3 plus 4. 3 plus 4 in Z5 is what? It is 7 actually. So it will become 2 when you do a remainder. So you have 1 into 2. So that is equal to 2. And let's try out the calculation on the other side of the distributive property. What is A into B? A into B is 1 into 3, which is 3. And what is A into C? Which is 1 into 4, which is 4. So when you add 1 into 3 plus 4, you'll again get 2. So basically what we are trying to show here is that in the Zn set, these properties are satisfied. Zn is the set of integers modulo n, and we are able to show that the addition property is commutative. Also, the distributive property holds, and these properties also hold, right? So basically, an interesting fact here is that in Zn, two integers, or not two integers actually, two non-zero numbers can be multiplied together to get 0. So that is one way in which Zn is different from Z. Different from Z. How? For example, let's look at Z4. Z4 is the set of integers following in these residue classes, right? Here, if you do 2 into 2, what is 2 into 2 in Z4? It is actually 4, but 4 will be written as 0, right? So 2 into 2 is equal to 0 in Z4. But obviously in Z, which is the set of regular integers, you will never have two non-zero numbers which will be multiplied to get a 0, right? So this is one way in which Zn is different from Z. However, if n is prime, then this can never happen. This can never happen. What can never happen? Two non-zero integers cannot be multiplied to get a 0. Why? So if it was Z5, think of that as 0, 1, 2, 3, 4. Is it possible for us to multiply two non-zero integers in this? Basically 1 into 2 or 1 into 3, anything between these four numbers and get a multiple of 5. The only way you would get a 0 is if you ended up with a multiple of 5, but that is not possible because 5 is a prime number. If two numbers from inside could be multiplied to get a 5, then that would be the factorization of 5. So the only way you can write 5 as a product of two numbers is 1 into 5. There is no other way, right? So since 1, 2, 3, 4 is here and there is no 5 here, it is impossible to multiply two numbers which are non-zero inside the set and get 0 as the output, right? So in that way, if n is prime, you will get back the same property that you have with the regular set Z of integers, right? Zn is different from Z only if n is not prime, right? So these are some basic properties. One more property that we can look at is another difference basically between Zn and Z. Another difference between Zn and Z. So what we can see is that in Zn, the number of roots of a polynomial equation f of x equal to 0 can sometimes be greater than the degree of the equation. We will take an example. So let's say we are looking at Z8, right? And we have the equation x square minus 1 equal to 0. So what is the degree of this equation? Degree of the equation is 2. If we were working in normal Z, we would say that it cannot have more than two roots, right? And we would say the two roots are plus or minus 1, right? However, you can show that x square minus 1 equal to 0 has 4 roots in Z8. What are the 4 roots? You can see 1, 3, 5, 7. What is 1 square minus 1? That is equal to 0 in Z8. 3 square minus 1 is 9 minus 1, which is 8, which is equal to 0 in Z8. 5 square minus 1 is 25 minus 1, 24, which is also divisible by 8. So 24 is congruent to 0 in Z8, right? And similarly, 49 minus 1, 48, right? So you are able to see that there are 4 roots for this quadratic equation in Z8, right? So that is another point of difference between the set Z8 and the set of normal integers Z, right? Again, similar to the previous property, if 8 was a prime number, if n was prime, this property would not be true. If it was Zn and n was prime, then a degree 2 equation will have only 2 or less than 2 roots, right? So these are some of the things that I wanted to bring out before we start our discussion of groups. So the next class will be about introduction to groups. We will try and do videos quite frequently, and I will try and cover all the theory that is required for IIT JAM Maths, which is basically this. So the outline of the syllabus for us is this. We want to discuss groups, cyclic groups, abelian groups, non-abelian groups, permutation groups, then normal subgroups, quotient groups, and then we look at Lagrange's theorem for finite groups. Lagrange's theorem for finite groups. Group homomorphisms and isomorphisms. Group homomorphisms. We'll also be looking at Sylow's theorems here. Isomorphisms and Sylow's theorems. So basically, this is the syllabus for the set of lectures that I will be presenting over the next few weeks. And hopefully this will be a good introduction for anybody who is struggling with the subject. I am also learning on the way, so it should be useful for all of us. And hopefully you will like the content that I'll be presenting. Please like and share the video, subscribe to the channel so that I can continue to provide free content. That is my request to all of you, and hopefully I'll see you in the next class.